Welcome, everyone, to TechDaily.ai. Just before we jump in, a quick word about our sponsor. This discussion is brought to you by Stonefly. They're your trusted solution provider and advisor for, well, pretty much everything. Enterprise IT storage, backup disaster recovery, hyper-converged setups like VMware, Hyper-V, Proxmox clusters, AI servers, even turnkey security with SA365, plus public and private cloud solutions. Do check them out at stonefly.com for more info.
Okay, so diving in, when you first look at a Linux setup, you see these weird folder names, right? Bin, etc., USR. It honestly just feels like a jumble of old abbreviations.
Oh, absolutely. It looks completely archaic at first glance, but, if you're doing any kind of development, scripting, sysadmin work, or honestly, even if you're just curious about how things really work under the hood, understanding the why behind the structure, that's probably the biggest shortcut to actually getting comfortable with Linux. And that's exactly what we're setting out to do today. We want to break down this Linux file system hierarchy, the FHS, starting right from the very top, from the root.
We're not just listing folders. We're trying to get at the philosophy behind how Linux organizes, well, everything.
Precisely, because when you understand why it's structured this way, you start to see the priorities. Things like security, stability, keeping different parts of the system separate so they don't interfere with each other. And look, this isn't just academic theory, it's super practical knowledge. It changes how you troubleshoot. You go from guessing to knowing where to look.
Right. So let's start where it all begins.
Yeah.
The absolute single starting point, the root directory, that single forward slash.
And slash, yeah. That's the trunk of the whole tree. Everything, absolutely everything, branches out from there. And the really key concept, especially if you're coming from, say, a Windows background, is this idea of a single unified file system.
Yeah, that's a big shift. In Windows, you have your C drive, your D drive, maybe a USB stick shows up as E. They're all separate little worlds. Exactly. Linux works differently. There are no drive letters. Doesn't matter if it's your main hard drive, a second drive, a USB key, a network share. It all has to be attached or mounted somewhere under that single root / Garo. It forces everything into one big logical structure.
Okay, and that brings us straight to maybe the first point of confusion for a lot of people. The difference between Saro and root. They sound almost the same, but they're totally different things.
They really are. So the single slash is, like we said, the starting point for the entire operating system's file structure. But root, that's /root, is just a specific folder inside that structure. It's the home directory, the personal workspace, specifically and only for the superuser, the administrator account known as root.
And I guess the reason for tucking the admin stuff away in root instead of, say, home root alongside regular users, that has to be about security, doesn't it?
Primarily, yes. It's about isolating the administrator's configuration files, scripts, personal data away from where regular users live. Think about it. If the home directory somehow got compromised or filled up, you wouldn't want that to affect the admin's critical files needed to fix the system. It's separation by design. Really fundamental.
Okay, so we've got the root, the main trunk. Let's look at the branches closest to it, the real core stuff needed just to get the system up and running. That brings us to bin and spin.
Right, bin. That stands for binaries, essential binaries, actually. These are the absolute minimum command line tools you need. Things like ls to list files, cfp to copy, mv to move, cat to view files. The really basic stuff you need for system maintenance, booting up, or if you're stuck in recovery mode.
And the key thing about bin is these tools have to be there right away, even if other major parts of the system, like maybe us layers, aren't available yet.
That's exactly it. They need to be accessible, even in a minimal state, like single user mode. They're the tools the system might need to, well, fix itself. Then you have SWIN, which holds system binaries. These are more specialized tools, usually for system administration tasks. Things like checking file systems with SPENC, managing network interfaces, mounting partitions, shutting the system down safely.
So bin is the basic user toolkit. SPIN is more the admin's toolkit, needing super user powers, usually. But hang on, why is something like mount in spin? Don't regular users sometimes need to see what's mounted?
Good question. Gets to the philosophy. The standard says spin is for tools that change the system's state, like actively mounting or unmounting something. Well, yes, modern systems often configure things so users can run commands to view mount information, putting the core mount command in spin historically reinforced that messing with file systems is primarily an administrative task. It helps prevent accidental system-wide changes by regular users.
Got it. Okay, but these commands in bin and spin, they don't exist in isolation. They need support code, right? Which leads us to lib.
Exactly. Lib is where the shared libraries live. So when a command in bin, say else, needs to do something complex like read directory information, it doesn't contain all that code itself. It calls a function stored in a shared library file located in lib. Think of them like DLLs and Windows reusable code modules that save space and memory because lots of programs can use the same library.
And we sometimes see lib32 or lib64 in there too. That's just for supporting different processor architectures, 32-bit versus 64-bit.
Precisely. It ensures compatibility, and also really important inside lib are the kernel modules. These are like little pieces of driver code, maybe for your specific network card or graphics card. The kernel can load these modules dynamically on demand to add functionality without needing a full system reboot. It's like the kernel's own plugin system, really.
Okay, now for probably the most confusing one for newcomers, the usery. The name suggests user, but it's almost never where your personal documents go. What's the real story with OSR or Unix system resources?
Yeah, that name is misleading today. Historically, though, Unix system resources made more sense. Back when disk space was incredibly precious and expensive, the root partition was kept absolutely tiny, just the bare essentials to boot. Unisr was often on a separate, much larger disk partition. And that was where the bulk of the actual applications, their libraries, system documentation, maybe even source code resided.
So it wasn't user data, but more like software for the user, functionality they'd interact with.
Exactly that. It holds the applications and utilities that make the system actually useful for day-to-day work, but which aren't strictly needed just to boot or repair the system. This separation also has modern benefits. Since the code in Unisr doesn't change often on a stable system, you can sometimes mount that whole partition as read-only, which adds a layer of security against malware trying to modify core applications.
And because of that history, OSR kind of mirrors the root directory structure. It has its own sbin, uslib, etc. How does the system know which bin to use?
Well, the system uses the path environment variable to find commands, but the fundamental distinction holds. Bin contains the absolute essentials for booting and recovery, while sbin holds the vast majority of user-installed software and utilities that assume a fully running system. The goal is always to keep that root partition lean and bootable, even if something goes wrong with a much larger sbin partition.
That philosophy separation for stability seems to carry right over to the next critical directory.
Boot. Conceptual simple, but absolutely vital. This folder holds everything the system needs before the main Linux kernel even starts running properly. You'll find the kernel image itself in here, the initial RAM disk, that's the initrid or initrams file, and the configuration files for the bootloader, like grub's grub.cfg, which tells the system how to start the kernel.
And the warning label on boot should be huge, right? Messing around in here is asking for trouble.
Oh, definitely. It's like performing surgery. If you damage that initrid file, which is a temporary mini file system loaded into memory, just to let the kernel access the real drives, your system just won't boot, period. That's why, especially on servers or systems with encrypted disks, boot is often put on its own small, separate, unencrypted partition. Ensures the bootloader can always find those critical startup files.
So once the system has booted, thanks to boot, and the kernel is running, it needs its operating instructions, its configuration, and that brings us to the system's control center, etc.
Yeah, configuration central is a good way to put it. The name's origin is debated, maybe, etc., maybe something else. But people often think of it now as editable text configuration, which is pretty accurate. Most files in here are plain text config files. This directory really is the brain of the system's configuration.
All system-wide settings live here. Network setup, how services start, user account policies, how drives are mounted automatically.
That's right. Key files like etc password, user account info, though passwords aren't usually stored there anymore, or etc stab, which tells the system how to mount partitions at boot. Because they're mostly text, admins can inspect and change them easily. But the flip side is that a tiny typo in an etc file can have huge consequences. Break networking, stop a service from starting, prevent logins. You have to be careful.
Okay, system's running, it's configured. Now users need their own space to actually do stuff. And that naturally leads us to home.
Home is pretty straightforward. It's the designated area for regular users' personal files. If your username is Alex, you typically get a directory home Alex, and that's your domain. All your documents, downloads, project files, personal settings, they live there.
And keeping this separate from the system files seems critical.
It is, for a couple of big reasons. First, backups and management. It's easy to back up all user data just by grabbing the home directory without touching the core OS files and etc. or OSRs. Second, security and permissions. Normally, user Alex can only write files inside home Alex. They can't easily mess with system files or another user's files, say, in HomeBob. It enforces separation.
And inside our own home directories, that's where we often find all those hidden files, the ones that start with a dot.
Ah, yes, the dot files. Things like .bashrc, .profile, or maybe a .config directory. These store your personal application settings and shell customizations. Your command history, custom aliases, editor themes, desktop appearance, all that stuff gets saved in dot files. They're hidden by default just to keep your main home directory view clean. Otherwise, it'd be cluttered with dozens of config files you rarely need to touch directly.
Okay, let's shift gears a bit. We've covered the main places where files are stored on disk. Now let's look at the more dynamic parts of the system, the places that represent hardware or things happening right now. Starting with dev.
Dev, for device files. This directory is maybe the clearest example of that core Linux idea. Everything is a file. Your hard drives, your keyboard, your mouse, your virtual terminals, even system memory. They all get represented as special files within dev.
So if I were to say read from devsda, I'm essentially reading raw data directly from my first hard drive using the standard file interface.
Pretty much, yes. That's the interface.
Yeah.
These aren't normal files stored on the disk itself, though. The kernel creates them dynamically when the system boots, representing the hardware it detects. And we usually distinguish between block devices like hard drives, devsda, dev vmello, and one, which handle data in chunks or blocks, and character devices like keyboards or serial ports, devds0, which handle data as a stream of characters. Treating hardware like files makes programming much simpler. You can often use the same basic read-write operations.
That seems incredibly powerful. But what about seeing what the system is doing right now? Which programs are running, how much CPU they're using? That takes us to these fascinating virtual file systems, proc and sys.
Right, virtual is the key word here. These directories don't represent files actually stored on your hard drive. They are generated on the fly, in memory, by the kernel. They provide a real-time window into the kernel state and the processes it's managing. Proc is primarily the process file system.
And those numbered directories inside proc, those numbers are the process IDs, the PIDs of running programs.
Exactly. Every running application, every background service gets a unique PID. If you want to know details about process 1234, say how much memory it's using, the files it has open, its command line arguments, you look inside the proc 1234 directory. Tools like top or htop are constantly reading files within proc to give you that live view of system activity.
And its partner, sys, what's its focus?
Sys is also virtual, but it's more focused on the structure of the system's hardware and the kernel's view of devices. It's organized hierarchically based on how devices are connected. You might see directories for PCI buses, USB devices, CPU cores, network interfaces. While proc is more about running software, sys is more about the hardware and kernel subsystems.
What's really interesting about sys, you mentioned, is that you can sometimes write to files in there. That sounds different.
It is, and it's a powerful feature for system tuning. Certain files within sys act as control knobs for kernel parameters or device settings. For instance, you might be able to adjust CPU frequency scaling policies, control the brightness of your laptop screen, or change power management settings for a USB device by simply echoing a specific value into the corresponding file in sys. It's like having a control panel for the kernel exposed through the file system.
Okay, staying with these dynamic in-memory locations, let's talk about run. Why do we need this?
Run is for runtime variable data. The crucial aspects are, 1, it's temporary. Everything in run is wiped clean on reboot. 2, it's typically mounted as a temps, meaning it exists entirely in RAM, making access incredibly fast.
So why not just use Team for this kind of temporary stuff? Why a separate run that lives in RAM?
Speed and purpose. Run is specifically intended for information that running processes need right now. Things like socket files for inter-process communication, IPC, lock files to prevent conflicts over shared resources, process IDs for running daemons. By putting these in superfast RAM via run, processes can communicate and coordinate very quickly without hitting the much slower disk I/O. It's vital, especially during system startup and for high-performance services.
And that leaves TEAMP as the more general-purpose temporary area.
Exactly. TP is the traditional place for temporary files created by users or applications, things that don't need to survive a reboot and don't need the guaranteed RAM speed of run. But because TP is often world-writable, anyone can create files there, it needs a special trick to maintain order.
Ah, right, the sticky bit.
The sticky bit. It's a clever permission setting on the TMP directory itself. It means that even though anyone can create a file inside TMP, only the owner of a file, or the root user, can actually delete or rename that file, It stops users from messing with each other's temporary files or accidentally deleting something important a system process put there. It keeps the public space usable.
Okay, nearly there. Let's clarify the mountain points. We have media and eminent. This distinction often trips people up.
Yeah, it can be confusing. The main difference boils down to automatic versus manual. Media is where modern desktop Linux systems typically automatically mount removable devices. You plug in a USB stick, insert a CD/DVD, connect a camera, the system usually detects it, and mounts it under a subdirectory within media, like media username is b-driven name, making it easily accessible.
And MNT is the opposite.
Pretty much. MNT, for mount, is the traditional generic mount point reserved for temporary manual mounts done by the system administrator. If you need to mount another internal hard drive for data recovery, or temporarily connect to a network file share using a command line tool, you typically create a directory inside mnt, like mrecovery or mnetworkshare, and mount it there yourself. It's for admin tasks, not everyday user access to removable media.
Got it. Now, for data that changes a lot, especially on service logs, caches, queues, that brings us to VAR.
VAR, for variable data. This is super important because it holds files that are expected to grow or change frequently during normal system operation. The classic example is var log, where all the system logs are written. But you also find things like web server caches, email queues waiting to be sent, printer spool files, data that's dynamic.
And var log is definitely the first place any admin looks when something goes wrong.
Absolutely. And because logs, especially on busy servers, can grow very large very quickly, var is often put on its own separate disk partition. This is critical. It prevents runaway log files or a full email queue from completely filling up the root file system, which could crash the whole system. Separating var protects the core OS.
Makes sense. And sitting alongside var, sometimes we see SRV. What's its role?
SRV is for service data. The idea is if your server is providing a specific service like hosting websites, serving files via FTP, maybe version control repositories, the actual data for those services should live in SRV. So your website's HTML files might be in SRV www, your FTP files in SRV FTP. It separates the service's content from its configuration, which would still be in etc. And it's variable data like logs, which would be in var.
Keeps things nicely organized. And lastly, the up directory.
Opt for optional application software packages. This is often used for third-party or proprietary software that doesn't follow the standard Linux packaging conventions or file system layout. Think of large, self-contained commercial applications, maybe a database system or a specific piece of scientific software. Installing them into opt application name keeps all their files bundled together, separate from the core system files managed by the package manager in us.
Yeah, it stops manually installed software from potentially overwriting system files or causing conflicts. It's a clean way to handle external packages.
When you step back and look at it all, this whole file system hierarchy isn't random at all. It's incredibly logical. It's a structure that evolved over decades, carefully designed to separate the critical, unchanging parts of the OS from the parts that change constantly, from user data, from hardware interfaces, from temporary files. That separation is really the key to Linux's reputation for stability and security.
And for anyone using Linux, whether you're coding, administrating, or just exploring understanding this map, it's foundational. It really is. Knowing what goes where helps you predict behavior, diagnose issues way faster, write better scripts. It just unlocks a deeper level of understanding.
Okay, so think about this. If the FHS is all about this careful separation, static system files here, user data there, logs over there, what does the growing importance of these dynamic RAM-based directories like run and proc tell us? It kind of suggests that for modern Linux, maybe the speed of communication between running processes happening instantly in memory is becoming just as critical, maybe even more critical for performance than the traditional ordered structure on the disk. It's like parts of the OS are becoming less like stored files and more like .live data streams. That shift in focus towards speed is a really fascinating bit of engineering, isn't it?